Take an ordinary kitchen teaspoon and imagine filling it with material so impossibly dense that it would weigh 6 billion tons, the same mass as Mount Everest, crushed into something small enough to stir your coffee. Today, we're going on an impossible journey to the heart of a neutron star, where gravity is so strong it bends space and time, where magnetic fields could rip the iron from your blood from 1,000 miles away, and where matter exists in states that we can barely comprehend. If you're fascinated by the extreme physics of our universe, make sure to subscribe to this channel and hit that notification bell. And here's something I've been wondering. If you could safely observe any extreme phenomenon in the universe up close for just 1 minute, what would you choose? Drop your answer in the comments below. I will pin the most creative answer. Now let's begin this incredible journey. Before we dive into the unimaginable interior of a neutron star, we need to understand what these objects are and how they come to exist. A neutron star is what remains after a massive star, at least 8 times heavier than our Sun, exhausts its nuclear fuel and dies in a spectacular supernova explosion. But this isn't just any death, it's one of the most violent events in the universe, where the very fabric of matter is transformed into something alien and bizarre. When a massive star runs out of fuel, it faces a catastrophic crisis. For millions of years, the star maintained a delicate balance between 2 opposing forces, the outward pressure from nuclear fusion in its core and the inward pull of its own gravity. Fusion creates energy that pushes outward, while gravity pulls everything inward. As long as the star has fuel to burn, these forces remain in equilibrium. But when the fuel runs out, gravity wins, and it wins catastrophically. In less than a second, faster than you can blink, the star's core collapses. The outer layers of the star, suddenly without support, come crashing down at speeds approaching a significant fraction of the speed of light. When this collapsing matter hits the incredibly dense core, it bounces back, creating a shockwave that rips the star apart in a supernova explosion visible across millions of light years. The explosion is so bright, it can outshine an entire galaxy for weeks. But while the outer layers of the star are blown into space, enriching the universe with heavy elements that will one day form new stars and planets, the core faces a different fate. The pressure becomes so intense that it overcomes one of the fundamental forces of nature. Protons and electrons, the building blocks of atoms, are crushed together with such force that they merge, forming neutrons and releasing a flood of ghostly particles called neutrinos. What remains is a neutron star, a city-sized sphere of matter so dense that normal physics breaks down. These objects typically measure only about 12 to 15 miles across, yet they contain more mass than our entire Sun. To put this in perspective, imagine compressing everything in our solar system, the Sun, all the planets, every asteroid and comet, into a sphere the size of Manhattan. That's the kind of density we're talking about. The numbers involved in neutron star physics are so extreme they lose meaning without context. The surface gravity is about 200 billion times stronger than Earth's. If you could somehow stand on a neutron star's surface, which you couldn't for reasons we'll explore, you would weigh about 200 billion times your Earth weight. A marshmallow dropped from a height of 1 meter would hit the surface with the energy of a nuclear bomb. Your body would be instantly flattened into a layer of particles thinner than an atom. The formation of a neutron star represents one of nature's most extreme recycling programs. The iron in your blood, the calcium in your bones, the oxygen you breathe, all these elements heavier than hydrogen and helium were forged in the cores of massive stars and distributed through space by supernova explosions. When we study neutron stars, we're not just examining exotic physics, we're looking at the cosmic forges that created the very atoms that make up our world and ourselves. But here's where things get truly strange. A neutron star isn't really made of neutrons in the way we typically think of particles. The pressure is so intense that the very concept of individual particles starts to break down. Matter enters a regime where quantum mechanics and general relativity, the 2 great pillars of modern physics, collide in ways we don't fully understand. It's as if the universe is performing an experiment that we can't replicate in any laboratory on Earth. The discovery of neutron stars reads like a detective story spanning decades. In 1934, just 2 years after the neutron itself was discovered, astronomers Walter Baade and Fritz Zwicky proposed that supernovae might create incredibly dense objects made primarily of neutrons. This was pure speculation based on theoretical physics. No one had any evidence such objects actually existed. It seemed too extreme, too bizarre to be real. For over 30 years, neutron stars remained a theoretical curiosity, something that might exist but couldn't be detected with the technology of the time. Then, in 1967, a graduate student named Jocelyn Bell Burnell made one of the most important discoveries in astronomy. While using a radio telescope to study quasars, she noticed strange, regular pulses of radio waves coming from a specific point in the sky. The pulses were so regular, arriving every 1.337 seconds, that she and her advisor initially wondered if they had detected signals from an alien civilization. They even nicknamed the source LGM-1 for Little Green Men. But as more of these pulsing sources were discovered, it became clear they were natural phenomena. The pulses were coming from rapidly rotating neutron stars, now called pulsars. As these incredibly dense objects spin, they emit beams of radiation from their magnetic poles. Like a cosmic lighthouse, when the beam sweeps past Earth, we detect a pulse. The discovery of pulsars provided the first direct evidence that neutron stars actually existed, confirming theoretical predictions made decades earlier. Since then, we've discovered over 3,000 pulsars in our galaxy alone. Each one is a natural laboratory where matter exists under conditions we can't create on Earth. The fastest spinning pulsar, PSRJ-17, 48-2446 AD, rotates 716 times per second. Think about that. This city-sized object containing more mass than our Sun completes 716 full rotations every second. The surface at its equator moves at about 1/4 the speed of light. Modern telescopes have revealed neutron stars in incredible detail. The NICER telescope, the Neutron Star Interior Composition Explorer, mounted on the International Space Station, can measure the size and mass of neutron stars with unprecedented precision by analyzing the X-rays they emit. The LIGO and Virgo gravitational wave detectors have captured the ripples in space-time created when two neutron stars collide, giving us insights into their internal structure that would have seemed like magic just decades ago. In August 2017, astronomers witnessed one of the most spectacular events ever observed: the collision of two neutron stars 130 million light-years away. The event, designated GW1-70817, was detected first as gravitational waves, ripples in the fabric of space-time predicted by Einstein a century ago. Within seconds, telescopes around the world and in space swiveled to observe the aftermath across the entire electromagnetic spectrum, from radio waves to gamma rays. This single event, lasting just minutes, produced more gold and platinum than the mass of Earth. The collision created elements that can't be formed any other way, spraying them into space where they'll eventually be incorporated into new stars and planets. It's humbling to realize that the gold in jewelry, the platinum in catalytic converters, and many of the rare elements in your smartphone were likely forged in neutron star collisions billions of years ago. The collision also confirmed something remarkable about the speed of gravity. The gravitational waves and the light from the collision arrived at Earth within seconds of each other after traveling for 130 million years. This proved that gravity travels at the speed of light, just as Einstein predicted. It's mind-boggling to think that we can test fundamental physics using events that occurred when dinosaurs roamed the Earth, with the results reaching us just a few years ago. Now let's begin our journey into the heart of a neutron star. As we approach from space, the first thing we'd notice is how small it appears. Despite containing more mass than our Sun, a typical neutron star is only about 12 miles across. You could drive across it in 20 minutes if there were a road. But don't let the size fool you. This tiny sphere warps space and time around it more dramatically than anything else except black holes. The gravitational field around a neutron star is so intense that it significantly bends light. As we get closer, we'd see the entire universe appear to distort around us. Stars would seem to shift position, and if we look back at where we came from, we'd see light bent into strange arcs and curves. This gravitational lensing is so strong that if you stood on a neutron star's surface, impossibly of course, you could see part of the back of your own head as light from behind you curves around the star. Time itself behaves differently near a neutron star. Due to gravitational time dilation, clocks run slower in strong gravitational fields. On the surface of a neutron star, time passes about 30% slower than in deep space. If you could somehow spend an hour on a neutron star's surface and then return to Earth, you'd find that about an hour and 20 minutes had passed for everyone else. This isn't science fiction, it's a real consequence of Einstein's general relativity, confirmed by countless observations. Speaking of mind-bending journeys through space and time, if you're fascinated by the extreme scales and distances in our universe, you might enjoy my video on how long would it take to reach each planet in our solar system. It really puts into perspective just how vast space is, even in our own cosmic backyard. The link is in the description below, but for now, let's continue our impossible journey into the neutron star itself. As we descend toward the surface, we encounter the magnetosphere, a region of space dominated by the neutron star's magnetic field. And what a magnetic field it is! The strongest magnets on Earth used in MRI machines and particle accelerators generate fields of about 10 to 20 Tesla. A typical refrigerator magnet is about 0.01 Tesla, but a neutron star's magnetic field can reach 100 million to 1 quadrillion Tesla. That's a 1 followed by 15 zeros. These magnetic fields are so strong they affect the very nature of matter and space. In such intense fields, atoms become distorted, stretched into long, needle-like shapes. The vacuum of space itself becomes birefringent, meaning it can split light like a prism. Virtual particles, quantum fluctuations that normally pop into and out of existence too quickly to detect, become real, creating a seething quantum foam around the star. If you had iron in your blood, which you do, and somehow got within 1,000 miles of a magnetar, a neutron star with an especially strong magnetic field, the magnetic forces would literally rip the hemoglobin molecules apart. At closer distances, the magnetic field would disrupt the atomic structure of your body, turning you into a stream of particles. These fields are so strong they can crack the neutron star's own crust, causing starquakes that release more energy in a fraction of a second than our sun emits in years. Now we reach the surface, though calling it a surface is somewhat misleading. The outermost layer of a neutron star is thought to be an atmosphere, only a few centimeters thick, made of the lightest elements that haven't been crushed into heavier forms. Below this incredibly thin atmosphere lies the outer crust, and this is where things start to get weird. Really weird. The outer crust is composed of atomic nuclei arranged in a crystalline lattice, swimming in a sea of electrons. But these aren't normal atoms. The gravitational pressure has crushed them into configurations that can't exist anywhere else. The nuclei are neutron-rich isotopes, many of which would be wildly unstable under normal conditions but are held together by the immense pressure. This crystal is the strongest material in the known universe, about 10 billion times stronger than steel. As we descend through the crust, the pressure increases exponentially. About 1 meter below the surface, the pressure exceeds anything we can create in laboratories on Earth. The atomic nuclei begin to deform, stretching and merging in ways that challenge our understanding of nuclear physics. This is where theoretical physics meets observational astronomy, where equations on a blackboard describe matter in states that existed nowhere else in the universe. At a depth of about half a mile, we reach the inner crust, and here the universe gets even stranger. The pressure is so intense that neutrons begin to drip out of the atomic nuclei, creating a superfluid of neutrons that flows without friction. This neutron superfluid can do things that seem to violate common sense. It can flow uphill, pass through solid matter, and create vortices that persist indefinitely. If you could somehow stir this superfluid, it would keep swirling forever. The inner crust is also where we encounter nuclear pasta. Yes, that's the actual scientific term. The competition between nuclear forces and electromagnetic forces creates structures that resemble different types of pasta. There are phases called gnocchi, blob-like structures, spaghetti, rod-like structures, lasagna, sheet-like structures, and even anti-spaghetti, rod-like holes in nuclear matter. These phases represent different ways matter organizes itself under extreme pressure, and they're not just theoretical curiosities. They affect how heat and magnetic fields move through the star. The nuclear pasta layer is incredibly important for understanding neutron stars. It's thought to be the strongest material in the universe, even stronger than the crystalline outer crust. The way this pasta layer breaks and reforms during starquakes might explain the glitches we observe in pulsar timing, sudden changes in rotation speed that happen when the crust cracks and angular momentum is transferred between different layers of the star. As we continue our descent past the crust, we enter the outer core at a depth of about 1 to 2 miles. Here, matter exists in a state that physicists call degenerate matter. The pressure is so intense that the Pauli exclusion principle, a fundamental rule of quantum mechanics that says two fermions can't occupy the same quantum state, becomes the dominant force resisting further compression. Matter here doesn't behave like anything in our everyday experience. The outer core is primarily composed of neutrons with a small fraction of protons and electrons, but these particles don't behave as individuals. They form a quantum fluid where the properties of the whole can't be understood by looking at individual particles. Superfluidity and superconductivity, states of matter where resistance to flow disappears, are thought to be common here. These quantum effects on a stellar scale create phenomena that seem almost magical. One of the most fascinating aspects of the outer core is the possibility of Cooper pairs, neutrons that pair up and move together like dancers in perfect synchronization. This pairing, similar to what happens in superconductors on Earth, allows neutrons to flow without any energy loss. The entire core might be a giant superconductor, carrying currents that have flowed for millions of years without diminishing. The density in the outer core is almost incomprehensible. We're talking about 500 trillion grams per cubic centimeter. That's 5, followed by 14 zeros. A sugar cube of this material would weigh about 500 million tons on Earth. At these densities, the very concept of empty space between particles loses meaning. The neutrons are packed so closely that they're almost touching, creating a continuous quantum fluid. But the outer core holds even more mysteries. Some theories suggest that at these densities, neutrons might break down into their constituent quarks, creating a quark-gluon plasma, similar to what existed in the first microseconds after the Big Bang. Other theories propose exotic particles like hyperons, particles containing strange quarks, might form. Each possibility would dramatically affect the star's properties and behavior. The temperature in the outer core can reach hundreds of millions of degrees, hotter than the center of the sun. But temperature here doesn't mean what it does in our everyday experience. In such dense matter, heat is carried by quantum excitations, particle interactions, that have no analog in normal matter. The cooling of neutron stars over millions of years provides clues about these exotic processes, as different cooling rates suggest different types of particles and interactions in the core. As we venture deeper, approaching the inner core, we enter the realm of true mystery. This is where our understanding of physics begins to break down, where competing theories make wildly different predictions about what we might find. The inner core of a neutron star, beginning at about 6 to 8 miles from the surface, represents one of the final frontiers in physics, a place where matter exists in states that challenge our most fundamental theories. The pressure here exceeds 1 followed by 35 zeros pascals. To put this in perspective, the pressure at the bottom of Earth's Mariana Trench is about 100 million pascals. The pressure in the neutron star's inner core is a trillion times greater. At these pressures, the very nature of matter might fundamentally change. Neutrons themselves might dissolve into their constituent parts, creating forms of matter that existed only in the first fraction of a second after the Big Bang. One possibility is that the inner core contains a quark soup, a plasma of up and down quarks no longer confined within individual neutrons. In normal matter, quarks are always confined within particles like protons and neutrons. The strong force that binds quarks gets stronger as you try to pull them apart, like a rubber band that never breaks. But at the densities in a neutron star's core, quarks from adjacent neutrons overlap so much that they might move freely, creating what physicists call quark matter. If quark matter exists in neutron stars, it would be the only place in the modern universe where quarks roam free. This state of matter, called a quark-gluon plasma, has been briefly created in particle accelerators like the Large Hadron Collider, but only for tiny fractions of a second and in microscopic amounts. In a neutron star, this exotic matter might exist stably for millions of years, offering a natural laboratory for studying the strong force under extreme conditions. But quark matter is just one possibility. Some theories suggest even more exotic forms of matter might lurk in neutron star cores. Strange quark matter containing strange quarks in addition to the up and down quarks found in normal matter might be more stable than nuclear matter. If this is true, neutron stars might actually be strange stars, made entirely of strange quark matter with just a thin veneer of normal matter on the surface. The possibility of strange matter has profound implications. If strange matter is truly the most stable form of matter, then contact between strange matter and normal matter could trigger a conversion, turning normal matter into strange matter. Some physicists have speculated about strangelets, small chunks of strange matter that might be created in neutron star collisions and drift through space. While this sounds like science fiction, it's a serious area of research with experiments designed to detect such exotic particles. Another exotic possibility is that neutron star cores might contain color superconductors. Despite the name, this has nothing to do with visual color, but rather with the color charge that quarks carry, the property that governs the strong force. In a color superconductor, quarks would pair up in a way analogous to electrons in a normal superconductor, creating a state where the strong force flows without resistance. This would be a fundamentally new phase of matter, never before observed. Some theories go even further, suggesting that the extreme conditions in neutron star cores might create entirely new types of particles. Hypothetical particles like H-debaryons, containing 2 up, 2 down, and 2 strange quarks, or pentaquarks, containing 5 quarks, might be stable at these densities. Each new type of particle would change the equation of state, the relationship between pressure and density, affecting the star's maximum mass and size. The inner core might also harbor dark matter. While we typically think of dark matter as diffuse and weakly interacting, some theories suggest it could accumulate in the extreme gravitational field of a neutron star. If dark matter particles can interact with normal matter, even slightly, they would sink to the core over millions of years. The presence of dark matter would affect the star's cooling rate and maximum mass, potentially providing a way to detect dark matter through astronomical observations. One of the most mind-bending possibilities is that neutron star cores might contain regions where the normal laws of physics break down entirely. At densities approaching the Planck density, where quantum gravitational effects become important, space and time themselves might become quantized, broken into discrete units rather than continuous dimensions. We simply don't have a theory that can describe matter under these conditions. The mystery of neutron star cores isn't just academic curiosity. Understanding what happens at these extreme densities is crucial for answering fundamental questions about the universe. The maximum mass of a neutron star, somewhere between 2 and 3 times the mass of our Sun, depends critically on the nature of matter in the core. Stars heavier than this maximum collapse into black holes, so understanding neutron star cores helps us understand the boundary between neutron stars and black holes. Recent observations have provided tantalizing clues about neutron star interiors. The detection of a neutron star with a mass of 2.17 solar masses, PSRJ 0740-6620, puts constraints on the equation of state. Some theories that predicted lower maximum masses have been ruled out. Similarly, the gravitational wave observations of neutron star mergers provide information about how neutron stars deform under tidal forces, revealing clues about their internal structure. The NICE mission has measured the sizes of several neutron stars with unprecedented precision, finding that they're slightly larger than some theories predicted. A typical neutron star with 1.4 times the mass of our Sun has a radius of about 13 kilometers. This might not sound like much of a difference from earlier estimates, but it has profound implications for what type of matter exists in the core. Larger neutron stars suggest stiffer equations of state, possibly ruling out some exotic matter theories. But perhaps the deepest mystery is how neutron star matter transitions from the crust to the core. There's no sharp boundary, but rather a gradual transition where matter becomes increasingly exotic. Understanding this transition is crucial for interpreting observations of neutron star oscillations, glitches in pulsar timing, and the cooling rates of young neutron stars. Each observation provides a piece of the puzzle, but we're still far from a complete picture. The study of neutron star interiors connects the smallest and largest scales in physics. The behavior of quarks and gluons, particles smaller than 1/millionth of a billionth of a meter, determines the properties of neutron stars that are miles across and can be observed from thousands of light years away. It's a beautiful example of how the universe is interconnected across vastly different scales. What makes neutron stars particularly valuable for physics is that they're stable. While particle accelerators can briefly create extreme conditions, neutron stars maintain these conditions for millions of years. They're natural laboratories where we can study matter under conditions that would require impossibly large amounts of energy to create on Earth. Every neutron star in our galaxy is an experiment in extreme physics that has been running for potentially billions of years. The cooling of neutron stars provides another window into their mysterious interiors. When a neutron star first forms in a supernova, its core temperature can reach 1 trillion degrees, 60,000 times hotter than the Sun's core. Over millions of years, it cools by emitting neutrinos and photons. The rate of cooling depends sensitively on what particles exist in the core and how they interact. By observing neutron stars of different ages and measuring their temperatures, we can infer properties of matter that we could never study directly. Young neutron stars, only thousands of years old, can still have surface temperatures of millions of degrees. The Cassiopeia A neutron star, formed in a supernova observed on Earth around 1680, has cooled faster than expected, suggesting exotic cooling mechanisms in its core. Perhaps Cooper pairs of neutrons are breaking and reforming, carrying away energy as neutrinos, or perhaps more exotic particles are involved. Each observation adds constraints to our theories. The magnetic fields generated within neutron star cores add another layer of complexity to this cosmic puzzle. While we observe the external magnetic fields of neutron stars, which are already unimaginably strong, the fields generated in the core might be even more intense. The motion of charged particles, protons and electrons in the outer core, or charged quarks if quark matter exists, creates currents that generate these fields. Understanding how these fields are sustained over millions of years requires knowing exactly what particles exist in the core and how they move. Magnetars, the most magnetic objects in the known universe, present an extreme case. Their surface magnetic fields reach 1 quadrillion times Earth's magnetic field, But the internal fields might be 100 times stronger still. These internal fields store enormous amounts of energy, occasionally releasing it in what's called a magnetar flare. The largest observed magnetar flare, detected in December 2004 from SGR 1806-20, released more energy in 1/10 of a second than our Sun emits in 100,000 years. The source of magnetar fields remains hotly debated. Are they generated by a dynamo effect where the motion of conducting fluids in the core creates and amplifies magnetic fields? Or are they fossil fields, remnants of the original star's magnetic field that was amplified during core collapse? The answer depends on what kind of matter exists in the core and whether it can support the necessary currents and superconducting states. Let me share something that perfectly illustrates the extreme physics at work in neutron star cores. In 2017, physicists calculated what would happen if you could somehow remove a teaspoon of matter from the center of a neutron star and bring it to Earth. The instant you removed the confining pressure of the surrounding material, this teaspoon of matter would explode with the force of several hundred nuclear bombs. The neutrons, no longer held together by immense pressure, would decay and the entire mass would expand violently. This thought experiment reveals something profound. The matter in neutron star cores exists in a delicate balance between enormous pressure and extreme density. Remove either factor and the entire structure becomes unstable. It's as if the star is holding together through sheer force of will, maintaining states of matter that can't exist anywhere else in the universe. The neutron star is essentially a giant atomic nucleus held together by gravity instead of the strong nuclear force. The equation of state, the relationship between pressure, density, and energy in matter, becomes crucial at these extremes. On Earth, we're familiar with simple equations of state, like the ideal gas law. But in neutron star cores, the equation of state involves complex interactions between quantum mechanics, nuclear physics, and general relativity. Different theories predict different equations of state, and each leads to different predictions about neutron star properties. Recent theoretical work has revealed something surprising. There might be a phase transition in neutron star cores, similar to how water transitions from liquid to ice. As pressure increases toward the center, nuclear matter might suddenly transition to quark matter. This transition could be smooth or abrupt, creating a hybrid star with a nuclear matter outer core surrounding a quark matter inner core. The interface between these phases would be one of the strangest surfaces in the universe, a boundary between two fundamentally different states of matter. If such phase transitions exist, they could explain several puzzling observations. Some neutron stars show sudden increases in their spin rate called anti-glitches, where the star briefly spins faster before settling back. These might occur when the inner core, spinning at a different rate than the crust, suddenly couples to it through changes in the phase transition boundary. It's like two gears that suddenly mesh, transferring angular momentum between the star's layers. The study of neutron star cores has become a collaborative effort between astronomers, nuclear physicists, and particle physicists. Observations from telescopes like NICER, Chandra, and gravitational wave detectors provide data about neutron star masses, radii, and deformability. Nuclear physicists use this data to constrain theories about nuclear matter at extreme densities. Particle physicists study fundamental interactions that might create exotic particles in neutron star cores. Together, they're assembling a picture of matter under the most extreme conditions. One of the most exciting developments in recent years is the use of gravitational wave astronomy to probe neutron star interiors. When two neutron stars spiral together and merge, they emit gravitational waves that carry information about their internal structure. As the stars approach, tidal forces deform them, and the amount of deformation depends on how stiff or soft the matter is inside. By measuring these tidal deformations through gravitational waves, we can determine the equation of state. The first neutron star merger detected by gravitational waves, GW1-70817, provided groundbreaking constraints on the equation of state. The data suggested that neutron star matter is moderately stiff, not as soft as some exotic matter theories predicted, but not as stiff as others. This single observation ruled out several competing theories about neutron star composition, demonstrating the power of multi-messenger astronomy. But the merger also revealed something unexpected. After the collision, instead of immediately collapsing into a black hole, the merged object survived for at least a few seconds as a hypermassive neutron star. A neutron star heavier than any that could exist in isolation, held up temporarily by rapid rotation. During those seconds, it might have created matter in states that never existed before or since, providing a glimpse of physics beyond our current understanding. The quest to understand neutron star cores also drives research in nuclear physics laboratories around the world. Facilities like the Relativistic Heavy Ion Collider at Brookhaven National Laboratory and the Large Hadron Collider at CERN create tiny droplets of quark-gluon plasma by smashing heavy atomic nuclei together. While these plasmas last for only fractions of a second, they allow physicists to study the properties of quark matter, information crucial for understanding whether similar matter exists in neutron star cores. Theoretical physicists use supercomputers to simulate nuclear matter at extreme densities. These simulations, based on quantum chromodynamics, the theory describing quarks and gluons, are incredibly computationally demanding. Even the most powerful supercomputers can only simulate small numbers of particles for brief periods. Yet these simulations are providing insights into how quarks interact at high densities, helping predict whether quark matter or more exotic states exist in neutron star cores. The connection between neutron star physics and the early universe is profound. In the first microseconds after the Big Bang, the entire universe was as dense as a neutron star core. By studying neutron stars today, we're glimpsing conditions that pervaded the entire cosmos 13.8 billion years ago. The quarks and gluons that might exist in neutron star cores today were once everywhere, filling all of space. Neutron stars are cosmic time capsules, preserving conditions from the universe's infancy. This connection goes even deeper. The elements created in neutron star mergers, gold, platinum, uranium, and others, are the same elements that make modern technology possible. The phone or computer you're using to watch this video contains elements forged in the cores of colliding neutron stars billions of years ago. We're literally made from the ashes of these extreme events, our existence dependent on physics at the edge of comprehension. Let me share something that illustrates the human side of neutron star research. In 1967, when Jocelyn Bell Burnell discovered the first pulsar, she was a 24-year-old graduate student. Her discovery revolutionized astronomy, yet when the Nobel Prize was awarded for the work in 1974, it went to her advisor and another senior scientist, not to her. This injustice highlights how science, for all its objectivity, is still a human endeavor subject to the biases and imperfections of any human activity. But Bell Burnell's story also shows the importance of curiosity and persistence. She noticed something unusual in the data, a signal that could easily have been dismissed as interference, and pursued it. That curiosity led to the discovery of neutron stars, objects that challenge our understanding of matter and space. It's a reminder that the greatest discoveries often come from paying attention to details that don't quite fit, from asking, "What's that?" instead of moving on. Today, thousands of scientists around the world work on neutron star physics, from observational astronomers tracking pulsars across the electromagnetic spectrum to theorists developing equations to describe exotic matter. Each contributes a piece to the puzzle. The graduate student analyzing pulsar timing data might be detecting glitches that reveal how superfluids behave. The physicist running simulations on a supercomputer might be discovering how quarks form Cooper pairs. Together they're unraveling one of nature's deepest mysteries. The technology we use to study neutron stars has advanced dramatically in recent decades, but it still faces fundamental limitations. We can never visit a neutron star, never sample its matter directly, never perform controlled experiments on it. Instead, we must be detectives, piecing together clues from light that has traveled for thousands of years, from gravitational waves that ripple through the fabric of space, from neutrinos that pass through Earth as if it weren't there. Every observation is precious, every data point a window into physics we can barely imagine. Modern pulsar timing has reached extraordinary precision. The best atomic clocks on Earth are accurate to about 1 second in 300 million years. But by tracking millisecond pulsars over years or decades, astronomers have created natural clocks even more precise. Some pulsars can be timed to within 100 nanoseconds, 100 billionths of a second. This precision allows scientists to detect tiny changes in the star's rotation, revealing processes happening deep inside the core. When a pulsar glitches, suddenly speeding up by a tiny fraction, it provides a glimpse into the interaction between the star's crust and its superfluid interior. The superfluid neutrons in the core don't participate in the star's gradual slowdown. They keep spinning at their original rate, like a gyroscope maintaining its orientation. When enough angular momentum builds up, the crust cracks. The superfluid suddenly couples to the crust, and the entire star speeds up momentarily. These glitches are like earthquakes that reveal Earth's internal structure, except these starquakes release energies that dwarf anything geological. The Vela pulsar, one of the most studied objects in our galaxy, glitches roughly every 3 years. Each glitch is slightly different, providing information about the superfluid's properties, the crust's strength, and how energy flows between different layers. By studying hundreds of glitches across different pulsars, scientists are building a statistical picture of neutron star interiors. It's like trying to understand the interior of a piano by listening to it from the outside. Challenging, but possible with enough careful observation. X-ray observations have revealed another window into neutron star cores through oscillations. Just as seismologists study Earth's interior by analyzing earthquake waves, astronomers study neutron star interiors by observing how they vibrate. When neutron stars undergo starquakes or accrete matter from companion stars, they ring like bells, oscillating at specific frequencies determined by their internal structure. Different core compositions predict different oscillation modes, allowing observations to constrain theories. The most dramatic oscillations occur during type Wood X-ray bursts, thermonuclear explosions on neutron star surfaces when accreted hydrogen ignites. During these bursts, oscillations with frequencies of 300 to 600 Hz appear in the X-ray emission. These oscillations might be caused by hotspots on the spinning surface or by actual vibrations of the star. Either way, they provide information about the star's mass, radius, and internal structure that can't be obtained any other way. Binary pulsars, neutron stars orbiting another star, provide yet another way to probe their interiors. As these systems orbit, the neutron star's gravity tugs on its companion, and the companion's gravity tugs back. By precisely measuring the orbital motion, astronomers can determine the neutron star's mass with incredible accuracy. The Hulse-Taylor binary pulsar, discovered in 1974, has allowed scientists to measure its masses to within 0.1%, the most precise measurement of a neutron star's mass ever achieved. Mass measurements are crucial because the maximum possible mass of a neutron star depends entirely on what's in the core. If the core contains exotic matter like hyperons or kaons, particles containing strange quarks, the maximum mass would be lower, perhaps around 1.5 solar masses. If the core is primarily neutrons with perhaps some quark matter, the maximum mass could be 2.5 solar masses or higher. Every neutron star we find above 2 solar masses rules out theories that predict lower maximum masses. The discovery of PSR J0348 plus 0432, a pulsar with a mass of 2.01 solar masses, was a game-changer. Many theories predicting exotic matter in neutron star cores couldn't explain how a star could remain stable at this mass. Then came PSRJ 0740 plus 6620 at 2.14 solar masses, and more recently, measurements suggesting some neutron stars might exceed 2.5 solar masses. Each discovery narrows the possibilities for what can exist in the core, but here's where the mystery deepens. While more massive neutron stars seem to rule out soft equations of state with exotic matter, other observations suggest neutron stars might be larger than expected, which favors stiffer equations of state. Reconciling these apparently contradictory observations requires sophisticated models where the core might transition from one type of matter to another, or where the equation of state changes behavior at different densities. Nature, it seems, doesn't make things simple. The thermal evolution of neutron stars provides another crucial constraint. A newly formed neutron star has a core temperature of about 1 trillion degrees. Over the first day, it cools to about 100 billion degrees by emitting neutrinos. Over the next 100,000 years, it continues cooling to about 10 million degrees. Different core compositions predict different cooling rates because different particles interact with neutrinos in different ways. If a neutron star core contains only neutrons, protons, and electrons, the cooling should be relatively slow, taking millions of years to cool below 1 million degrees. But if exotic particles like hyperons or kaons exist, or if quarks are deconfined, these particles would produce additional neutrinos through various processes, accelerating the cooling. By observing neutron stars of known ages and measuring their surface temperatures, we can test whether fast or slow cooling processes dominate. The Cassiopeia A neutron star has provided a particularly intriguing case. Observations between 2004 and 2013 showed it cooling about 4% faster than expected. This rapid cooling might indicate that neutrons in the core recently transitioned to a superfluid state, a transition that would emit a flood of neutrinos. If confirmed, this would be the first direct evidence for superfluidity in neutron star cores, a quantum effect on a stellar scale that seems almost impossible. Recent observations with the Hubble Space Telescope and Chandra X-ray Observatory continue to monitor Cassiopeia A, watching how its temperature changes over decades. These observations are testing detailed predictions about superfluid transition temperatures, neutron pairing gaps, and neutrino emission mechanisms. It's remarkable that we can use observations of a star 6,000 light-years away to test theories about quantum mechanics at densities impossible to achieve in any laboratory. The detection of neutrinos from supernovae provides yet another way to study neutron star formation. When supernova 1987A exploded in a nearby galaxy in February 1987, it was close enough and bright enough that neutrino detectors on Earth captured about 24 neutrinos from the collapse. These neutrinos, carrying information about the conditions in the forming neutron star, matched theoretical predictions remarkably well, confirming our basic understanding of core collapse. Future neutrino detectors, like the proposed Hyper Kamiokande in Japan and the Deep Underground Neutrino Experiment in the United States, will be sensitive enough to detect thousands of neutrinos from a supernova in our galaxy. If a massive star explodes nearby, and statistically one should every few decades, these detectors would capture a treasure trove of information about neutron star formation, including details about the equation of state, neutrino physics, and the transition from normal nuclear matter to the exotic states in neutron star cores. The study of neutron star interiors also connects to fundamental questions about the nature of the strong force. Quantum chromodynamics, the theory describing how quarks and gluons interact, is well tested at low energies and densities, where quarks are always confined within particles like protons and neutrons. But at the densities in neutron star cores, we're probing a regime of QCD where our computational tools break down and our understanding becomes uncertain. One of the deepest mysteries in physics is the behavior of the strong force at high densities. Does it allow quarks to become deconfined, moving freely through the core? Or do quarks remain bound in neutrons even at these extreme densities? The answer determines whether neutron stars have quark matter cores or remain nuclear matter all the way through. Neutron star observations might help answer this question before particle accelerators can reach equivalent energies. Lattice QCD, a computational technique where space-time is divided into a grid and quantum field equations are solved numerically, has made progress in calculating properties of nuclear matter at high densities. But the computational requirements are enormous, and current simulations can only handle densities somewhat below those in neutron star cores. As supercomputers become more powerful, these simulations will provide increasingly accurate predictions about what phases of matter exist at different densities. The possibility of color superconductivity in neutron star cores represents one of the most exotic predictions of QCD. In normal superconductors, electrons pair up and move without resistance through a material. In color superconductors, quarks would pair up based on their color charge, creating a state where the strong force flows without resistance. Multiple types of color superconducting phases are theoretically possible, each with different properties and different effects on neutron star structure. If color superconducting quark matter exists in neutron star cores, it would dramatically affect several observable properties. The star would cool faster due to neutrino emission from quark pairing. The maximum mass would be higher because color superconductivity makes matter stiffer. Most intriguingly, the transition between nuclear matter and color superconducting quark matter might create a sharp density discontinuity that could affect gravitational wave signals from neutron star mergers. The strange quark matter hypothesis takes these ideas even further into the realm of the exotic. Normal matter contains only up and down quarks, the lightest types. But at the densities in neutron star cores, strange quarks might be energetically favorable. Strange quarks are heavier than up and down quarks, which normally makes them unstable and short-lived. But in the extreme conditions of a neutron star core, having a mixture of up, down, and strange quarks might actually be the lowest energy state. If strange quark matter is truly more stable than nuclear matter, then what we call neutron stars might actually be strange stars, objects made entirely of strange quark matter with just a thin crust of normal matter on top. This would fundamentally change our understanding of these objects. The transition from the normal matter crust to the strange matter interior would be sharp and dramatic, more like the surface of a lake than the gradual transition we'd expect in a conventional neutron star. Strange stars would have different maximum masses, different cooling rates, and different responses to rotation than conventional neutron stars. Some researchers have suggested that certain observed properties of neutron stars, like how some cool faster than expected or how some seem smaller than predicted, might be evidence for strange stars. But the case is far from settled, and most astronomers still favor conventional neutron star models. The truly mind-bending possibility is that of strange matter stability at normal pressures. Some calculations suggest that once strange matter forms, it might remain stable even without the crushing pressure of a neutron star. If this is true, a chunk of strange matter exposed to normal matter would convert it to strange matter in a runaway reaction. This sounds terrifying, but before you worry about Earth being converted to strange matter, know that this scenario is highly speculative, and most physicists consider it unlikely. Nevertheless, the possibility has led to interesting speculation about primordial strange matter. If strange matter could have formed in the early universe when conditions were hot and dense, chunks of it might still be wandering through the cosmos. These hypothetical strangelets would be incredibly dense, electrically neutral, and might pass through normal matter with little interaction. Some researchers have even suggested searching for strangelets by looking for tiny, extremely dense objects in cosmic ray detectors. The relationship between neutron stars and black holes represents another frontier in our understanding. There's a maximum mass for neutron stars, somewhere between 2 and 3 solar masses depending on the equation of state. Above this mass, not even the extreme pressure of degenerate matter can resist gravity, and the star collapses into a black hole. This mass limit, called the Tolman-Oppenheimer-Volkoff limit, depends critically on what's inside the core. Recent observations have found several neutron star candidates with masses right at this boundary. These objects might be the most massive neutron stars possible, or they might be the lightest black holes. Some might even be something in between, quark stars or hybrid stars with properties intermediate between neutron stars and black holes. Each discovery near this mass boundary provides crucial information about the equation of state at the highest possible densities. The first direct image of a black hole, captured by the Event Horizon Telescope in 2019, has inspired similar efforts to image neutron stars. While we can't see the interior of a neutron star, we might be able to map hotspots on their surfaces with such precision that we can measure their sizes and shapes. These measurements, combined with mass measurements from binary systems, would provide the strongest constraints yet on the equation of state. NASA has already made groundbreaking measurements of neutron star radii by observing X-ray pulsations from hotspots on rotating neutron stars. As the star spins, hotspots come into and out of view, and the exact pattern of brightness changes depends on how much the star's gravity bends light. By modeling these light curves, scientists can determine both the star's mass and radius, the two measurements needed to calculate its average density and constrain the equation of state. The results so far have been fascinating. PSRJ 0030 plus 0451, a millisecond pulsar, appears to have a radius of about 13 kilometers for a mass of about 1.4 solar masses. This is slightly larger than some theoretical predictions, suggesting that matter in neutron star cores is stiffer than the softest equations of state predict. But it's not as large as the stiffest predictions either, ruling out some nuclear matter models. Nature, it seems, chooses a middle path. Let me tell you about something that perfectly captures the international and collaborative nature of neutron star research. When the neutron star merger, GW 170817, was detected in August 2017, it triggered a cascade of observations involving more than 3,000 scientists from 70 observatories across all 7 continents. Gamma-ray satellites detected the initial burst. Optical telescopes in Chile saw the kilonova glow. Radio telescopes in Australia tracked the expanding debris. X-ray observatories watched the afterglow fade over weeks. This single event generated over 100 scientific papers in its first year, addressing everything from the expansion rate of the universe to the creation of heavy elements to the equation of state of neutron star matter. It was a triumph of multi-messenger astronomy using gravitational waves, electromagnetic radiation across all wavelengths, and possibly neutrinos to study the same event. This is how modern astronomy works, as a global collaboration where discoveries belong to all humanity. The data from that merger is still being analyzed, still yielding new insights. The gravitational wave signal during the final moments before merger showed how the stars deformed under each other's tidal forces, providing constraints on how easily neutron star matter can be compressed. The electromagnetic observations revealed the creation of about 10 Earth masses of gold and platinum, confirming that neutron star mergers are the primary source of heavy elements in the universe. But the merger also left behind a mystery. After the two neutron stars collided, there should have been either a black hole or a hypermassive neutron star supported by rotation. The observations suggested the latter, a neutron star heavier than any that could exist in isolation, spinning hundreds of times per second, generating magnetic fields stronger than any we've ever observed. This object existed for seconds to minutes before likely collapsing into a black hole, but during that brief existence, it might have created matter in states that never existed before or since. The possibility of observing more neutron star mergers in the future excites astronomers tremendously. LIGO and Virgo are being upgraded to detect such mergers from even greater distances. A proposed detector in India would help triangulate sources more precisely, and the planned space-based LISA detector, scheduled for the 2030s, would detect gravitational waves from orbiting neutron stars hours or days before they merge, giving astronomers time to point every available telescope at the event. Future observations might catch a neutron star in the act of collapsing to a black hole. The exact moment of collapse would reveal the maximum mass possible for a neutron star, which would immediately tell us whether exotic matter exists in the core. If neutron stars can be more massive than 2.5 solar masses without collapsing, it suggests relatively normal nuclear matter in the core. If they collapse at lower masses, it suggests exotic particles or quark matter, softening the equation of state. The study of neutron star interiors also has implications far beyond astrophysics. Understanding matter at nuclear densities is crucial for nuclear physics, with applications to nuclear reactors and nuclear medicine. The computational techniques developed to simulate neutron star matter have applications in materials, science, and chemistry. The precise timing of pulsars has led to new technologies for navigation and timekeeping. Science that seems purely abstract often yields practical applications in unexpected ways. But perhaps the most profound impact of neutron star research is philosophical. These objects force us to confront the limits of our knowledge. We've never observed quark matter, never touched strange matter, never seen a color superconductor. We're extrapolating our theories far beyond where we can test them directly. This requires both confidence in our theoretical framework and humility about our limitations. It's science at its most daring and most honest. The fact that we can study matter under these extreme conditions at all is remarkable. A civilization confined to one planet, unable to observe neutron stars, would have an incomplete understanding of physics. They might develop theories about quark confinement and the strong force, but they'd have no way to test those theories at the densities where the most interesting physics happens. We're fortunate that the universe provides these natural laboratories, scattered throughout our galaxy like cosmic experiments running for our benefit. Every neutron star is slightly different depending on how it formed, how old it is, and what it's experienced since birth. Some are isolated, spinning quietly in space. Others are in binary systems, accreting matter from companions and producing X-ray bursts. Some are millisecond pulsars, spun up to incredible speeds by accreting matter. Others are magnetars with magnetic fields so strong they crack their own crusts. Each type provides different information about neutron star physics. The diversity of neutron stars means we need a diverse set of observations. Timing observations reveal the star's rotation and how it changes. X-ray observations reveal surface temperature and emission from hotspots. Gravitational wave observations reveal internal structure and maximum mass. Each type of observation constrains different aspects of neutron star physics, and only by combining them all can we build a complete picture. The theoretical frameworks we use to understand neutron star cores represent some of the most sophisticated physics ever developed. Researchers must combine quantum field theory, which describes particles and forces at the smallest scales, with general relativity, which describes gravity and space-time at the largest scales. These two theories famously don't play well together. Combining them leads to infinities and contradictions. Yet in neutron stars, both are crucial and can't be ignored. This is why neutron star cores might hold clues to the ultimate theory physicists seek: quantum gravity. In most situations, you can use either quantum mechanics or general relativity and ignore the other. But at the Planck scale, where quantum effects and gravitational effects become equally important, both must be considered simultaneously. While neutron star cores don't quite reach the Planck density, they're the closest thing we have to a natural laboratory where both theories matter significantly. Some physicists speculate that if we understood neutron star cores completely, we'd be closer to understanding quantum gravity. The fact that we don't yet have a complete theory of neutron star interiors might not be a limitation, but rather an opportunity. Neutron stars might be telling us something fundamental about physics that we haven't yet learned to hear. Every puzzle they present might be a clue pointing toward deeper truths. The role of symmetry in neutron star physics is fascinating. In normal matter, various symmetries govern how particles behave: charge symmetry, time reversal symmetry, parity symmetry. But at extreme densities, some of these symmetries might break down. The presence of superfluid neutrons and superconducting protons represents a form of spontaneous symmetry breaking, where the system chooses a particular state out of many equivalent possibilities. Color superconductivity, if it exists, would represent an even more dramatic symmetry breaking. The color symmetry of quantum chromodynamics, which says that switching the color charges of quarks shouldn't change physics, would be spontaneously broken, just as electromagnetic symmetry is broken in normal superconductors. Understanding how and when these symmetries break could reveal fundamental principles governing all of physics, not just neutron stars. The relationship between temperature and phase transitions in neutron star cores adds another layer of complexity. As a neutron star cools over millions of years, the matter in its core might undergo phase transitions similar to how water freezes into ice. Hot, young neutron stars might have cores in different states than cold, old neutron stars. Some transitions, like the onset of superfluidity, are predicted to occur at specific temperatures, and observing cooling neutron stars might allow us to watch these transitions happen. The concept of nuclear pasta, those exotic phases I mentioned earlier that resemble gnocchi, spaghetti, and lasagna, deserves deeper exploration. These aren't just whimsical names, they describe real physical structures that should exist in the inner crust and possibly the outer core. The pasta phases arise from the competition between nuclear attraction, which wants to form dense clumps, and electromagnetic repulsion between protons, which wants to spread matter out. At lower densities in the inner crust, matter forms spherical blobs, the Gnocchi phase. As density increases, these blobs connect into rods, the spaghetti phase. At even higher densities, the rods connect into sheets, the lasagna phase. Then something fascinating happens. The geometry inverts. Instead of dense matter in an empty space, you get empty space in dense matter. This creates anti-spaghetti, where the pasta is actually tubes of empty space, and anti-gnocchi, where spherical bubbles of empty space float in dense matter. These pasta phases might be the strongest material in the universe, with breaking strains 10 billion times greater than steel. The crust can sustain enormous stress before fracturing, which is why neutron stars can have mountains, bumps on the surface, perhaps a few millimeters high, but containing as much mass as the Himalayas. These mountains create asymmetries that generate gravitational waves as the star rotates, carrying away angular momentum and slowly spinning the star down. The search for continuous gravitational waves from rotating neutron stars represents one of the frontiers in observational astronomy. While LIGO and Virgo were designed to detect transient events like neutron star mergers, they can also search for the steady signal from a single spinning neutron star with a slight asymmetry. No such signal has been definitively detected yet, but upper limits on their strength are already constraining how large neutron star mountains can be, which constrains the strength of the crust material. Let me share something that illustrates the interplay between theory and observation in neutron star physics. In the 1970s, theorists predicted that neutron stars should have superfluid interiors. This wasn't wild speculation, but a consequence of well-understood physics applied to extreme conditions. When neutrons are packed densely and cooled below a certain temperature, they should form Cooper pairs and become a superfluid. This prediction was taken seriously but couldn't be directly tested. We can't sample a neutron star's interior. Then came the glitch observations. Pulsars were seen to suddenly speed up slightly, an effect that could be explained if the superfluid interior was decoupled from the crust and occasionally transferred angular momentum to it. Suddenly, a theoretical prediction had observational support, but the story doesn't end there. Detailed modeling of glitches revealed that the superfluid properties had to be just right to explain the observations. This led to refined predictions about neutron pairing strengths and superfluid transition temperatures that could then be tested in nuclear physics experiments on Earth. This back and forth between theory, astronomical observation, and laboratory experiment exemplifies how science works at its best. No single approach provides complete answers. Theory predicts what should happen under extreme conditions. Astronomical observations test whether those predictions match reality. Laboratory experiments probe the underlying physics in controlled settings. Together, they build a consistent picture that explains phenomena across vastly different scales. The role of neutrinos in neutron star physics cannot be overstated. These ghostly particles, which barely interact with matter, dominate the energy budget of a neutron star for the first 100,000 years of its life. The star cools primarily by emitting neutrinos from its core, not by radiating light from its surface. Different processes in the core, neutron decay, quark interactions, Cooper pair breaking, produce neutrinos with different energies and rates, making the cooling curve a sensitive probe of core composition. Fast cooling processes, which involve exotic particles or quark matter, can make a neutron star cool dramatically faster than slow cooling processes involving only nucleons. The difference can be a factor of 10 or more in temperature after just 10,000 years. By measuring the temperatures of neutron stars with known ages, like those in supernova remnants, where we know when the star formed, we can determine whether fast or slow cooling dominates, constraining what particles exist in the core. But measuring neutron star surface temperatures is challenging. The stars are small and distant, making their thermal emission faint. Their surfaces are also strongly magnetized, creating hotspots and temperature variations that complicate interpretation. The spectra of neutron star atmospheres are affected by strong gravity and magnetic fields in ways we're still learning to model. Every temperature measurement comes with uncertainties that must be carefully understood. Recent observations with the Chandra X-ray Observatory and XMM Newton have measured temperatures for dozens of neutron stars, building a statistical picture of cooling across the neutron star population. Most seem to follow slow cooling, suggesting conventional nucleonic matter in their cores, but a few show evidence for fast cooling, hinting at exotic processes. The diversity of cooling rates might indicate that different neutron stars have different core compositions, perhaps depending on their mass or formation conditions. The magnetic field evolution of neutron stars adds another dimension to the puzzle. Young neutron stars often have relatively modest magnetic fields of about 1 trillion Gauss, still enormously strong by human standards but weak for neutron stars. Over millions of years, these fields can decay, with the magnetic energy being converted to heat. But some neutron stars, the Magnetars, have fields 1,000 times stronger, and we don't fully understand why. One theory suggests magnetars form when the proto-neutron star immediately after core collapse is rotating rapidly enough to drive a dynamo, a process where the motion of conducting fluids amplifies magnetic fields. The newly formed star, still hot and partly fluid, might generate enormous magnetic fields that become frozen into the solid crust as it cools. But testing this theory requires understanding how conducting fluids behave at nuclear densities, another problem that depends on knowing what particles exist in the core. The fields in magnetar cores might be even stronger than surface fields, possibly reaching 100 quadrillion Gauss. At these strengths, the magnetic pressure exceeds the material pressure, meaning the magnetic field actively shapes the star's structure. The core might be threaded with magnetic flux tubes, channels where the field is even stronger, creating a tangled topology that occasionally rearranges itself violently, producing the observed magnetar flares. These magnetic field structures affect how heat flows through the star. Thermal conduction is much easier along magnetic field lines than across them, creating temperature anisotropies. The surface temperature map of a magnetar probably shows hot and cold regions, determined by the internal magnetic field geometry. Future X-ray telescopes with imaging capabilities might be able to map these temperature variations, providing a window into the internal magnetic structure. The possibility of planets orbiting neutron stars adds a fascinating wrinkle to the story. Several pulsar planets have been discovered, including the first confirmed exoplanets ever detected, found around PSRB 1257+12 in 1992. These planets probably formed from the debris disk created during the supernova explosion or from a later collision. Any life on such planets would experience a very different environment than Earth, bathed in radiation from the pulsar, orbiting under skies illuminated by a star that's a small, bright dot rather than an extended disk. But here's a wild thought. Could pulsar planets provide a way to study neutron star interiors? As the pulsar's radio beam sweeps past a planet, it might scatter off the planet's atmosphere or magnetic field. The timing and polarization of these scattered signals could reveal properties of the beam, which in turn depends on the magnetosphere structure, which depends on the internal magnetic field, which depends on core composition. It's a long chain of inference, but astronomy often works through such indirect connections. The future of neutron star research is incredibly exciting, with new instruments and techniques promising to revolutionize our understanding. The Square Kilometre Array, a radio telescope currently under construction in South Africa and Australia, will be 50 times more sensitive than any existing radio telescope. It will discover thousands of new pulsars, including potentially rare systems like neutron star binaries or neutron stars orbiting black holes, each providing unique tests of physics under extreme conditions. The James Webb Space Telescope, while primarily designed for observing distant galaxies, might also contribute to neutron star science by observing supernova remnants and young neutron stars in unprecedented detail. Its infrared vision could reveal the environments around newly formed neutron stars, helping us understand their early evolution. Future X-ray telescopes like Athena and Lynx will have the sensitivity to detect thermal emission from neutron stars across the galaxy, building a comprehensive census of the neutron star population. The next generation of gravitational wave detectors will open entirely new windows on neutron star physics. The proposed Einstein telescope in Europe and Cosmic Explorer in the United States will be 10 times more sensitive than current detectors, able to detect neutron star mergers from when the universe was young. They might even detect continuous waves from spinning neutron stars with tiny asymmetries, revealing the internal structure through how mass is distributed inside the star. These future observations will test predictions that seem almost impossible to verify. Can we really determine the equation of state of matter at nuclear densities by listening to gravitational waves from colliding stars billions of light years away? Can we really map the internal magnetic field structure by watching X-ray pulsations from surface hotspots? The answer appears to be yes, and this is one of the marvels of modern astrophysics, that we can study the unstudiable through clever combinations of observations and theory. But beyond the scientific instruments, there's also the human element of discovery. Young scientists entering the field today will spend their careers unraveling neutron star mysteries. Graduate students analyzing data from NASA might make the observation that finally determines whether quark matter exists in cores. A postdoc running simulations might discover a new phase of nuclear pasta that explains pulsar glitch statistics. An undergraduate participating in a pulsar timing project might be the one who notices the anomaly that reveals superfluid properties. The democratization of astronomy through citizen science also plays a role. Projects like Einstein at Home use the computing power of hundreds of thousands of volunteers' computers to search for pulsars in radio and gravitational wave data. Citizen scientists have discovered pulsars that automated searches missed, contributing directly to our census of neutron stars. When the next nearby neutron star merger is detected, amateur astronomers around the world will point their telescopes at the sky, joining professionals in the greatest observational campaign in history. Let me tell you about one of the most profound questions neutron star research is helping to answer. What are the fundamental building blocks of matter? We often learn in school that atoms are made of protons, neutrons, and electrons. Then we learn that protons and neutrons are made of quarks. But are quarks truly fundamental, or are they made of something even smaller? And under what conditions do quarks behave as individuals versus being confined in particles? Neutron star cores might provide answers that particle accelerators can't. The Large Hadron Collider can create quark-gluon plasma for fractions of a second, but neutron stars maintain similar or even more extreme conditions for millions of years. They're natural particle accelerators operating at energy scales we can't achieve artificially. By observing how neutron stars behave, their masses, radii, cooling rates, and responses to rotation, we're probing the behavior of matter at energies beyond our technological reach. This connects neutron star physics to the deepest questions in physics. String theory, loop quantum gravity, and other attempts to unify quantum mechanics with general relativity make predictions about physics at extreme energies and densities. While we can't directly test these theories in most situations, their predictions about neutron star properties might be testable. A neutron star is effectively a cosmic laboratory for testing theories of everything. The possibility that neutron star cores contain dark matter opens another fascinating avenue. Dark matter, which makes up 85% of the universe's matter, remains mysterious. We know it exists from its gravitational effects, but we don't know what it's made of. If dark matter particles have even tiny interactions with normal matter, they would accumulate in neutron stars over millions of years, sinking to the core where their presence might affect observable properties. If you made this far, make sure to subscribe to the channel and give a thumbs up. And if you enjoyed this video, I am sure you will love this other one at the left side of the screen. Does gravity really travel faster than the speed of light? In this video, discover the mind-blowing science behind gravity's speed, from Newton's idea of instant action to Einstein's revolutionary theory of general relativity. See you there.